Okay, so it's 12 o'clock. Welcome everybody to another seminar in the IFIMAC-ICMM joint seminar series on condensed matter. My name is Pablo San Jose. I'll be chairing the session today. And it's my great pleasure to introduce our speaker today, Rui Silva, who will tell us about high-harmonic spectroscopy of strongly correlated and topological materials. This is a really exciting topic that deals with electron dynamics under intense electromagnetic radiation. It is often framed within the field of attosecond physics. And well, Rui is a young theoretical physicist that is specialized in this field, particularly on the response to very strong electromagnetic radiation of diverse electronic systems, for example, atomic gases or topological 2D materials. He's also a real wizard with numerical simulations and high performance computing. He graduated from the University of Porto in 2010 and then did a master's in theoretical and computational chemistry at the Universidad Autónoma de Madrid. And then in 2012, he began his PhD in the group of Professor Fernando Martín, also at UAM. On the topic of diatomic molecules under intense laser pulses. So already from this early stage, he began developing his skills and expertise in the simulation of extreme electron dynamics. Then when he finished his PhD in 2016, he moved to the Max-Born Institut in Berlin to the group of Professor Mikhail Ivanov, who's a prominent figure in the field of astrophysics, where he worked on high harmonic generation in solid state systems, which essentially is the broad subject of today's seminar. For his second postdoc, he moved back to UAM, to the group led by Johannes Feist at IFIMAC to study ultrafast molecular polaritonics. And it must be said that despite his young age, Rui has already published some outstanding works, including a number of well-cited Nature Photonics and PRLs. He was also recently awarded a LaCaixa Junior Leader Fellowship with a project starting this September at the crossroads between ultrafast optics and quantum materials. And we are very proud that he chose to join our theory group on quantum materials and technologies at the ICMM to carry out this project. Okay, so with this, I'll now pass it over to Rui. I just remind you that you can ask questions after the talk, and to do so, you just write them in the chat or preferably raise a virtual hand and ask the questions yourself. So go ahead, Rui.
Okay, thank you very much for your kind introduction, Pablo. And I would like also to thank the organizers for inviting me, and especially to Elsa Prada for inviting me to this talk. So the topic of my talk is high harmonic spectroscopy of strongly correlated and topological materials. And I'm currently working at the ICMM, at CSIC, in the group of theory of quantum materials. So as all works in science, nothing is done pretty much alone. So I've done this work alongside with Álvaro Jiménez Galán, currently at the National Research Council in Canada, also with Mikhail Ivanov and Olga Smirnova at Max-Born Institut, with Bruno Morim from Universidad Domingo in Portugal, and Fernando Martín at UAM, and also Igor Blinov and Alexei Robotsov at the Russian Quantum Center. So to begin with, I'm going to start with a brief introduction or a short course in condensed matter physics or in strong field physics in condensed matter physics. So to begin with, I would like just to brief mention what is nonlinear optics. And I would start with a quote from a book of Shen, The Principles of Nonlinear Optics. And in the first paragraph, he says that while linearization beautifies physics, it's nonlinearity that provides excitements to physics. So, and this is a very powerful tool. So in the linear regime, everything is beautiful, but in the nonlinear regime, we start to see things that are way beyond the analytical expressions, and we start to see things that occur in strong regimes. So imagine that you shine your sample imagine that you have your sample that is a gas or a solid with a laser field with a frequency omega, okay? In principle, if everything is linear, the radiation that is emitted is mostly around omega. So you don't have any kind of response on 2 omega or 3 omega. But if you start to increase the intensity or the strength of your laser field, you start to see nonlinear effects. So in the traditional way of nonlinear optics, you can write your polarization, the polarization of your material, as being a sum over a Taylor expansion over the powers of the electric field. So you have here, this would be if we cut just into until the linear term, we have just linear effects. But if we start to include these second order terms, these third order terms, we start to see nonlinear effects. In particular, for example, if we include this term, we start to see second harmonic generation that was discovered just 1 year after the invention of the laser field. And also, if we start to see like further effects like Kerr effect or further harmonic generation, and so on and so forth. And the intensity of the radiation of 2 omega, for example, is proportional to the intensity of your field to the power of the number of photons required for that process. For example, a second order process goes with the intensity of your field to the second power. So to observe very high harmonics, of course, what we need to have is that our intensity, the strength of our electric field must be very, very high. So this is a typical high harmonic generation spectrum. So people, after the invention of the laser, after the development of CPA, laser pulses started to be very, very intense. So when people were shining these laser pulses in atoms or in molecules, in gases, they start to see that the radiation that is emitted is strongly, strongly nonlinear. So as I said before, you expect that you have a power law. If you have an harmonic generation, this goes with the power of the intensity to the power of n. So you would assume that in a perturbative regime, you have that your harmonics decay exponentially with the order of the harmonic. But when people start to see high harmonic generation, they saw this kind of spectrum. So they saw that the harmonics were going to decay until the ionization potential of the molecule or the atom, and then be below the ionization potential until ionization potential plus 3 times the polynormative energy of the electron. They would see that the harmonics remain, or the intensity of the harmonics remain more or less constant. So this is a clear indication. So this plateau clearly indicates that your perturbative expansion fails, completely fails. So this kind of approaches to the polarization of your system fails. So you have strong nonlinearities in your system. How can we explain these strong nonlinearities of our system? So the first thing is to study how atoms or molecules are ionized when in presence of a very strong laser field where the frequency of the laser field is much, much smaller than the potential, the ionization potential. So in this case, when you shine a laser field in which the frequency of the laser field is much smaller than the ionization potential of your atom or your molecule, you have essentially 2 ways to ionize your atom or molecule. You have either multi-photon ionization, that is, you just pile up a bunch of photons until you reach the continuum threshold. And this is called multi-photon ionization. But if your field, if your electric field is so strong that it can tilt in a very abrupt way the potential felt by the electron, and if it is slow enough for that the electron can tunnel out this barrier, the electron can go and it can be ionized by tunneling ionization. And this was proposed in theory by Keldysh in the 60s in this Journal of Experimental and Theoretical Physics paper. So he was using this strong field approximation. And this strong field approximation is a quite dramatic and very, very far apart from our perturbation theory mindset. So it assumes that after ionization, the electron does not feel the molecular potential or the atomic potential. And this is in complete contrast with what we expect in perturbation theory, that the perturbation is our field, but here in strong field approximation, the perturbation really is your ionic potential after ionization, okay? So Keldysh defined an adiabaticity parameter that is more or less related with the tunneling time, the time that an electron takes to tunnel out, divided by the typical time of the frequency, the period of your laser pulse. And he arrived to this expression that goes with the square root of the ionization potential divided by 2 times the ponderomotive energy. And the ponderomotive energy is more or less the kinetic energy that an electron has in an oscillating field. So by doing this strong field approximation, Keldysh arrived to the conclusion that the ionization rate, when gamma is much smaller than 1, so this is the tunneling regime, that the ionization rate has an exponential behavior. So this is in complete opposition with what we expect with perturbation theory. On the other hand, if omega is much larger than 1, then you are in the multiphoton ionization regime. So your ionization rate goes with intensity of the field to the power of the number of photons that are required to ionize your atom or molecule. So essentially, we have 2 regimes for strong field ionization of atoms and molecules. So we have the multiphoton ionization, in which your Keldysh parameter is much larger than 1. And on the other hand, you have the tunneling ionization regime, in which gamma, this Keldysh parameter, is much smaller than 1. But how high harmonics are really generated? And this was well explained in this paper by Korkum in 1993, in which he established a model, the 3-step model, to explain in a semi-classical way what is the intuition behind the high harmonic generation in atoms. Okay, so the first step, imagine that this yellow line is your electric field, represents your electric field, and since here we have a maximum of electric field, we can tilt a lot our atomic or molecular potential. So in this instant of time, we can ionize. So once the electron is ionized, the electron will evolve freely in an oscillating electric field. And this is the strong field approximation. So we will have the acceleration of the electron in the continuum. So this electron will acquire some kinetic energy, and when the electric field changes sign, the electron can come back and recollide with the parent ion. And in this recollision, there is a certain chance of going back to the initial ground state. So in this process, you have an electron with a high kinetic energy that collides with the nuclei and can go to the ground state. And in this process, it liberates a photon with energy that is equal to the kinetic energy acquired in this strip plus the ionization potential. So what you are essentially doing is coming with a slow laser field, typically an infrared field, and you emit a photon with very, very high energy. And not only that, it's not only a very high and energetic, it's a very short pulse, because this process is very localized in time, okay? So So in experiments, people were seeing this kind of maximum, so that the maximum photon energy was proportional to 3 times the ponderomotive energy, and this scales with the intensity of the laser field. And also, you can use this kind of process to generate very short bursts of light with an attosecond duration. So in 2011, this process was discovered in solids, in bulk solids, in semiconductors. And this was a real game changer with respect to atoms and molecules. So now you have the opportunity. So the discovery of high-harmonic generation was in the late 80s. So all the high-harmonic generation field was developed for 20 years in atoms and molecules. And in 2011, this was discovered to be possible in bulk solids. So in bulk solids, now this opens the possibility of studying this process that allows you to have information about the attosecond electron dynamics in atoms and gases. But now you can see this in electron dynamics, but in solids. Okay. So in solids, this was discovered by Gmir in zinc oxide, and they saw that in contrast with atoms, the scaling of the cutoff goes with the strength of the field and not with the intensity of the field. And so this opens the opportunity, the window to study electronic dynamics in the attosecond time scale in bulk solids. So the discovery of this can open this new road for attosecond condensed matter physics. And since we know that in atoms we are quite limited, so our system is pretty much, so we saw a universal, almost universal behavior, but we know that in solids we start to see emergent phenomena. So like in this paper of Anderson, in which he introduced the concept of emergent phenomena, we know that when a bunch of atoms are together, they behave completely different from a single atom, from the behavior of a single atom. So now what we can do is to start to see things that we know from condensed matter physics, but now at ultra-fast timescales. So people start to see observation of dynamical Bloch oscillations. So you have such a large field that you drag your electron until the edge of the brilliant zone, and then you have these Bloch oscillations, and you see these in the high harmonic spectrum. Also, since this is a strongly nonlinear field, you drag your electron way beyond the parabolicity of the band. So you start to see the nonlinearities of the band, and also you can reconstruct optically the band structure. And also you can see an anisotropy of high harmonic generation in solids. So what is the origin of harmonics now in solids? So when you have a strong laser field, and strong, I mean the intensity or the strength of the laser field, but the photon frequency is very, very small, and it is much smaller than the band gap, the excitation to the valence band is dominated by Landau-Zinner tunneling. So imagine that you have your valence band that is completely full, and your conduction band that is initially completely empty. When you shine a laser field in the maximums of the electric field, you start to induce some population in the conduction band because you have Landau-Zinner tunneling. Once you do that, you have free electrons in the conduction band and free holes in the valence band, and they start to propagate each other accordingly with K is equal to the vector potential. So just the semi-classical equations of motion. And since an electron in a band has, since an electron in a band has a Bloch velocity that is given by the gradient of the band dispersion plus the anomalous velocity, you will start to see harmonics. Why? Because you enter in this K, this sign of omega t, because K is equal to A of t, so A of t is proportional to a sign. So you start to see some harmonics that are due to the current inside the conduction band. Another process that can originate harmonics is the interband harmonics. So you start to create an electron and a hole, they will propagate, and at some points they can recombine. And at this recombination, they can liberate a photon that is equal to the difference between energy between the conduction and the valence band. So today, what I'm going to talk about is how electron-electron correlation can affect this picture and how the topology of the band can also affect this picture. So topology of the band will enter into this term in the anomalous velocity, of course. So this is the outline, the menu.
Rui, I think we have a question from somebody in the audience. Do you care for questions now?
Yeah, now.
Okay. Okay, so please, Akashdeep Kambra, go ahead.
Yeah, thank you very much. In the last slide, it was not so clear to me how Landau's inner tunneling worked here, because I'm used to thinking of it as some sort of, being close to an anti-crossing or something. So can you say a little bit more about how the Landau's inner tunneling works in the system and what is the parameter being varied and so on?
So the Landau's inner tunneling is just because you have a field that is slow, and you can even think about a static picture. So you have a static electric field, and this static electric field can induce some tunneling to the conduction band. I don't know if it answers your question.
But the tunneling means I basically need a hybridization kind of. So the electric field is also causing the two levels to hybridize?
Yeah, I mean, yeah, so that's the thing. So if you would diagonalize this in an electric field that is a static electric field, so the electric field is so large that they will hybridize, and you can have transfer from population of the valence band to the conduction band.
Okay, I see. Okay, yeah. Thank you. Thanks.
Okay, so now this is the outline, the menu of for today, because before it was just a introduction to the topic. So first I will talk about time resolving the insulator to metal transition using high-harmonic generation. And this work was done in collaboration with Igor Blinov, Alexei Rubotsov, Olga, and Misha from the Max-Born Institut. So I was referring that I was going to talk about how electron-electron correlation affects this picture of high-harmonic generation in solids. And the first thing that can come to your mind is electron-electron correlation, just Hubbard model. So we can go to do what is the high-harmonic generation spectrum in a Hubbard model. And why Hubbard model? Because it is the simplest model in which electron-electron correlation is explicitly taken into account. It contains a lot of many-body physics. It can be solved exactly, at least in 1D, using exact elimination. And we don't have to assume any ad hoc assumptions for the electron-electron correlation. So when you have the Hamiltonian for the Hubbard model, you have just two terms. It seems a very simple Hamiltonian, and it's not. It's a very highly non-trivial Hamiltonian. And you have a hopping term in which you have, if you have only this term, you just have a single band. And you have a repulsion term. So each time you have two electrons at the same site. So you have electrons with spin up and spin down. And each time you have two electrons at the same site, you pay the price of U. So that is the repulsion Hamiltonian. So when you're when you are in the tight binding limit, you have that just a tight binding of one band. So since we are going to work in the half field system, so just with one electron per site, you are in the presence of a conductor. And since you are in the conductor, you have electrons in your conduction band that are going to be driven by the electric field in the conduction band, and they are going to originate intraband harmonics. On the other hand, in the atomic limit, in the limit where U goes to infinite, you only have the electrons are completely frozen because you don't have any hopping. And in the ground state, doubly occupied states are forbidden. And since we have this super exchange, we have the presence of short-range antiferromagnetic orders. So spins that are adjacent, they tend to be in a anti-parallel configuration. And this is the paradigm of a Mott insulator. When we shine a laser field and we have a strong electric field in this direction, in the direction of the lattice, we can start to force some electrons to hop and to create some doublons. So initially, all your sites, you have one electron per site because you have a Mott insulator, and suddenly you have some electric field that can be enough to tunnel to an adjacent site, creating a doublet. And now this doublet and this hole, they can propagate without paying any price because the energy was already given by the electric field. So if you have a strong enough laser field or a strong enough electric field, you can induce an insulator to metal transition. So you can do this with the bath ansatz in the 1D Hubbard model, and you can know what is the Mott gap and also what is the correlation length. And it was derived in this paper by Takashi Oka that the threshold field, so the electric field that is needed in order to create these double hole pairs, is just given by the Mott gap, that is the optical gap between the ground state and optical excitations, divided by 2 times the charge of the electron times this correlation length. So what we have done was to do some calculations using exact elimination and to simulate a potential 1D Mott insulator that is Strong-Schupp cuprate. So we have done exact elimination, we have used these parameters, and what we are going to do is to scan the values of U from 0 to 10 in order to see what is the difference between having a Mott insulator or having the tight binding and not uninterested. So here I show you this plot. So this plot, this is time, and each horizontal line is a calculation. And I'm showing you here what is the value in which time our calculation or our field goes beyond this threshold field. So what I'm plotting here is the spin-spin correlation. So what you can see is that until we reach this threshold field, so we have our laser field, and until we reach this threshold field, we don't have any kind of dynamics in the spin-spin correlation. But as soon as we go beyond this threshold field, we start to destroy this spin-spin correlation. So we go from a short-range antiferromagnetic to a paramagnetic. So this transition occurs only if our laser field can surpass this threshold field. And this can be also seen in the production of double hole pairs. Also, when you calculate what is the ground state population, you see that this transition occurs in one laser cycle. So this is really a subcycle phase transition. So the answer now is, can we trace this phase transition with optical response? So with high-harmonic generation? And the answer is yes. So when we look at how is our high-harmonic generation spectrum with when we scan the values of U of T, U divided by T0, we see that the harmonic emission is completely dominated in the regions of energy where we have these double hole pairs. So the harmonic emission is located between the Mott gap and Mott gap plus AT0, that is the bandwidth of your charge excitations. So this harmonic emission is completely different from what I've shown you in atomic case or molecular case. So, and since the harmonics are almost present, are only present in this region of energy, double hole pairs must be the responsible for the harmonic emission. And what we have seen is that when you do when you time resolve your high harmonic generation process, so now what I'm showing you is how harmonics are emitted within your poles. You see that harmonics, you see here this green, you see that harmonics are completely located when you are going under a phase transition. So you see here that the evolution of double hole pairs changes when you see harmonic emission. So by looking at the harmonic emission, you can trace when your phase transition is occurring. So it is just an optical breakdown. It is not, because we are destroying, we are changing completely our ground state population. We are destroying our short range ordering, magnetic ordering, and we are completely changing within one cycle of the pulse the properties of our system. So we are going from a short range antiferromagnetic material to a paramagnetic material. So we are in presence of a phase transition that can be looked or traced in time, in real time, using this high harmonic process. So the next topic is how can we obtain information from topological insulators or from the topology of the material using high harmonic spectroscopy. And this was done by Alvaro, Bruno, Olga, and Misha alongside with me. So when I think about a topological insulator, I think about Ferrero Rocher. So we have an insulating book that is a chocolate, and we have the conducting surface that is the aluminum foil. Okay, so in anomalous quantum Hall insulators that were introduced by Haldane, you have that your Hall conductivity is quantized, and this quantization is linked to the Berry curvature. So the integral of the Berry curvature along the first Brillouin zone gives you the Hall conductivity, and this Hall conductivity is quantized, and it is proportional to the Chern number. And as I've told you before, the semi-classical velocity of an electron in a band is not only the dispersion, the gradient of the dispersion of the band, but it also contains this term. And this term is called the anomalous velocity. So, but when we see this, we see that the velocity of the electrons, so the velocity relates to the current that allows you to see, that is the responsible for the harmonic emission. So can we see signatures of the Berry curvature in the harmonic spectrum? So, and these are just general relations. When we have inversion symmetry, the Berry curvature is a Hall function, and when we have time reversal symmetry is an invariant function. What we are going to do is to study the Haldane model. So this model is the workhorse of topological insulators. So we start with the graphene model, in which we have a honeycomb with a first just one hopping to the nearest neighbor, and we have this kind of band structure. Since we have inversion symmetry and time reversal symmetry, the Berry curvature is exactly 0 at all points of the Brillouin zone. When we introduce this on-site, this mass in the graphene model, so we have, for example, hexagonal boron nitride, we introduce a gap in K and K prime, and now our Berry curvature is no longer 0, but integrates to 0. Now, what Haldane have done was to introduce a next nearest neighbor hopping with a complex phase. And what this does is to break the time reversal symmetry, and now you are allowed to have an integral of your Berry curvature that is plotted here, and it will integrate to some finite value. So it is not 0 anymore. And indeed, when you see so this is when you change the parameter m. So this is the on-site energy of your atoms, and this is the phase of your complex T2, your next near neighbor hopping. You see that this is the phase diagram. So you have Chern number equals to 0 in this region, and we have Chern number equals to 1 and minus 1. And for example, we have chosen this point in which we have a trivial insulator, and what you see here is that the band structure is pretty much the same as in the case where you have a topological case. So this point is in the trivial part of the phase diagram, and this one is in the topological part of the phase diagram. And what you see despite of the fact that the band structure is pretty much the same, the Berry curvature is not. So what you see is that you see a change of the Berry curvature, the sign of the Berry curvature, near the K point, the point in which you close your band gap. So how can high-harmonic generation distinguish between the two phases? So when we have done calculations for the trivial and the topological case, and we see the intensity of the high-harmonic generation, we see that they are pretty much the same. So in this case, we use a laser that is polarized along gamma K. So you cannot see any difference between a trivial and the topological phase. So high-harmonic generation intensity is blind to the topological phase transition. But this is the intensity. What about the ellipticity of your high-harmonics? What about how your light rotates with respect to so how your light rotates? So how your light is polarized. So when we have done calculations, we have seen that the harmonic number one, the fundamental harmonic, does not change. So this is the ellipticity in this colored plot. So when you go through the phase diagram, you see that the ellipticity of the harmonic one does not change. But when you see high harmonics, so harmonic 3 or harmonic 9, you see that the ellipticity of your harmonic change sign. And what is the reason for this change of sign in the topological phase? So the reason is that in the trivial case, both linear, so both fundamental and high harmonics are dominated by the sign. So the ellipticity is dominated by the sign of the ellipticity of the Berry curvature, by the sign of the Berry curvature around K. Whereas in the topological phase, what we have is that high harmonics are indeed controlled by the sign of the Berry curvature, that change sign, as you can see here, but the first harmonic does not, because the first harmonic really feels this positive Berry curvature in the valence band, okay? Because you have a finite hole conductivity. So in trivial phase, linear and high harmonics, they have the same ellipticity. In the topological phase, they change ellipticity. So we can reconstruct by optical means this high harmonic ellipticity. So this phase diagram. So by looking at how the ellipticity of high harmonics compared with harmonic 1, we can know and reconstruct here the phase diagram of Haldane model. So the next one is light wave control of value polarization. So how we can use these strong fields now to control the value polarization in HPN or 2D TDMCs. So this was done alongside with Alvaro, Olga, and Lisha. So in valitronics, the goal is to engineer ways to populate either K or K prime, the two values that you have in, for example, in HPN, to encode information. So what we know is that linear polarized light can couples equally to both values. So we cannot shine a linear laser and expect that we have some value polarizations. On the other hand, we know that when we shine circular polarized light, we can selectively populate K and K prime. So if we shine light that is sigma plus, we can populate K here. And if we do with a different polarization, we just populate K prime. So the goal is to control the value state of that we induce with a strong laser field, but now on ultrafast timescales. And can we read this value polarization after that, after having some value polarization using nonlinear optical response? So our answer is to come, instead of using circular polarized light going sigma plus or sigma minus, we can just use two circular fields, omega and 2 omega that counter-rotate. So you have omega that goes in this direction, and you have 2 omega that rotates in the opposite direction. When you sum up the both pulses together, you have this kind of Lissajous figure, okay? And the relative phase, this phi, between the two pulses can rotate your triangle shape. So this is Lissajous figures can rotate in space by varying, by changing this phi. So by changing the time delay, we can change the way that the electric field acts on the different sublattice. As you can see here, this is in the real space, we can just superimpose this Lissajous figure. So we see that in this pulse addresses the A sublattice and the B sublattice on the same manner. But when you have phi equals to 0 or phi equals to pi, you address differently the A sublattice or the B sublattice. So what this pulse is really doing is to induce a complex T2 in the system, just like we have in the Haldane model. And the imaginary part of this effective T2 that we are inducing with our pulse is proportional to the cosine of phi. So by changing this phi, we can change the phase of T2, so we can change the way we interact with K or K prime. So when we have done calculations, and we have done calculations, for example, here I'm showing you 3 cases, the case where phi is equal to minus pi over 2, in which you are addressing K and K prime on the same way. So you see that the population at the end of the pulse is pretty much the same in K and K prime. On the other hand, if you came with this orientation or this orientation, what you have is that you are going to address K and K prime differently. So we will have here population on K prime and here population on K. So by changing the time delay between the two pulses, we can control the value polarization. And also what we have seen is that this value polarization, just like in the Haldane, is imprinted in the ellipticity of the high-harmonic. So I'm here varying this phi. So this is the same pulse. I'm just varying this phi. And you can vary this phi within a femtosecond time scale. So within a femtosecond time scale, you can go from K, value polarization in K, or value polarization in K prime. And the ellipticity of the harmonics, of the high harmonics, follow this trend. So you can go with a third pulse and probe what is the population, what is the value polarization that you induce it in your material. The next one is how can we use very short laser pulses to induce valuetronics? This work was done in collaboration with Alvaro, with Olga and Misha. And I've told you before that using linear polarized pulses, by using linear polarized pulses, you cannot distinguish between K and K prime. But this is in the long limit, in the limit where you have a long pulse. If we use very short single cycle pulses, we can obtain value polarization. And I'm going to try to convince you that even using linear polarized pulses, if they are short enough, you can induce some value polarization. So the idea is very simple. In a long pulse, when you have a maximum of the electric field, the vector potential is exactly equal to 0. But this is not the case when you have single cycle pulses. So for example, in this pulse, I'm showing here in black the electric field, you have 2 maximums of the electric field. So ionization, well, excitation to K and K prime will occur mainly in this instance of time. So in this instance of time, you will induce some population around K and around K prime. But since the vector potential is not 0 at that point, as we can see here, and they are exactly the same, what will happen is that this population is dragged, at the end of the pulse, will be dragged by this vector potential. So this black arrow is just representing this vector potential. And this is only streaking. So since K, so your crystal momentum is just equal to the K, your initial K, minus your effective potential at your initial time, you will drag your electrons from K to K prime and your electrons from K prime to gamma. So in this way, you see that you have some Wally polarization. So what we have done was to change this single cycle phase. So now what we are doing is really changing the internal phase of the single cycle pulse. And by changing the internal phase of the single cycle pulse, we see that we can induce some Wally hole conductivity, some Wally polarization. And then by looking also again at the intensity of the second harmonic, now we can read what is the Wally polarization that we have induced by looking at the intensity and also the phase of the second harmonic. To finish, I'm going just to briefly comment on a methodological paper, and this was done in collaboration with Fernando and Mikhail Ivanov. So when you try to calculate the nonlinear response of crystals, you have several methods. So you can go for TDDFT, that is very computational demanding, and results are very hard to interpret. You can solve the time-dependent Schrodinger equation, but in this framework, it's very hard to include the coherence terms. Or you can go to a semiconductor Bloch equations. And in this framework, it's very easy to interpret results, and it is also very easy to include excitonic and decoherence effects. But when you try to solve the semiconductor Bloch equations, you can solve it in two different pictures. So the velocity gauge, and in this velocity gauge, you have the advantage that all K points are decoupled, but then you need to include a lot of bands to converge your result. And also decoherence is not a straightforward thing. In length gauge, results are very easy to interpret. And also it's way easier to converge with respect to number of bands. But we require smooth transition dipole moments along the brilliant zone. And when you solve your band structure, you have a certain gauge freedom to choose the eigenstates along this brilliant zone. And since you can choose this randomly, for example, in an ab initio calculation, the DFT code just spits out the Kohn-Sham orbitals with random phase along the brilliant zone. This is problematic because then the transition dipole moments are going to be affected by this gauge freedom, and they can be completely chaotic in the brilliant zone. So how can we circumvent this problem? So how to deal with the wave function gauge freedom? So this is the gauge freedom that you have, that you can just multiply your wave function with respect to K with a phase that can be random in K, and this does not need to affect your results, but the transition dipole moments are affected by this. And since in numerics we want very smooth transition dipole moments, this is going to be problematic. So one solution is to try to create a smooth and periodic gauge, but this is very hard and model dependent, and it's especially hard when we have like a lot of band crossings, when we have a spaghetti of bands. This is a very, very difficult problem. And the problem is even bigger when the number of bands increases. So whole problems arise when you diagonalize K, H of K. So just like in molecular physics, what we need to use is, instead of using the bases that diagonalize H of K, you just get rid of this and deal with a diabatic basis. So our diabatic basis can be constructed using these maximum localized linear functions. So if you want to have details on this technique, just read this article on Review of Modern Physics. So it's a technique that allows you to extract localized linear functions from DFT calculations and allows you to map DFT calculation with a tight binding model. Then you can construct your Bloch functions with these linear functions, and if this linear function is very well localized, this Bloch function is going to be very, very smooth along K. So all the information then is stored in the, so in order to solve your problem, you just need to have these matrix elements of the Hamiltonian and these position operator matrix elements between the different Wannier orbitals. So in this gauge, all the transition dipole moments are going to be smooth. And then numerical propagation in the maximum localized Wannier function is way easier than trying to construct some ad hoc periodic gauge or trying to smooth out by hand. So to conclude, I've showed to you that we can use high harmonic generation to time resolve an insulator to metal transition. Also, you can use this high harmonic spectroscopy to see the phase transition in topological insulators, and you can use the ellipticity of the harmonics as a fingerprint of the Chern number. We can use strong fields to control the valley polarization that we have in our system using this delay, by varying this delay in a femtosecond time scale. And we can use these omega to omega pulses and also these very short single cycle pulses. And then this valley polarization can also be read using this high harmonic generation. And at the end, I show you that maximum localized Wannier functions can be used as a basis for solving the semiconductor Bloch equations. So with this, I would like to finish. I would like to thank LaCaixa, and most of all, I would like to thanks to all of you for your attention. So thank you all.
Thank you, Rui. Thank you very much. Everybody can express clapping with the virtual hand. Okay, so it's now time for questions. I see we have at least one question, again from Akasdip. So please go ahead. Can you unmute yourself or?
Yeah, thank you. Yeah, I can do that. Yeah, I had a question about the second work that you was mentioning. I think I got confused. Maybe I missed it at some point. The circularly polarized light can already differentiate between the valleys, right? So what is the high harmonics in this case?
Okay, the thing is that now you are not coming, okay, you are coming, usually you need to come with a resonant pulse, with a resonant circular pulse to either induce K or K prime. Right. Now your strong field, okay, I forgot to mention this. Your fields, your omega and 2 omega are non-resonant, okay?
Yeah, no, sorry, I meant the previous work, not this one, the one before.
Okay, sorry.
Where you were detecting the
ellipticity of the harmonics.
Right. So the ellipticity here, the information you say is in the ellipticity of the harmonics. My question is, would this information be already there in the resonant light or not? Yeah,
if you do. Okay, so the thing is that if you have the, you can do circular dichroism also. So indeed, after our paper, there was a paper doing this, doing the same, seeing the same things, but now it's circular dichroism, comparing the difference between sigma plus and sigma minus.
I see. Okay, thank you. Thanks a lot.
Okay, I see we have also a question from Elsa Prada. Please go ahead.
Hi, this was a great talk, Rui. Thank you very much. Can you put the last slide of conclusions?
Okay.
This is a very general question. I'm interested in the use of high harmonic spectroscopy for topological materials.
Yeah.
So if I understand correctly, you say that the harmonic intensity is almost blind to the topological phase transition, and then it's in this ellipticity of harmonics that you can detect the Chern number. So my question is, do you think this high harmonic generation is a good tool to detect in general topological materials?
Yeah,
or is it in general difficult?
Yeah, so the thing is that since high harmonic generation is always very sensitive to, for example, to the Berry curvature, because you drive your electron in the Brillouin zone, then you have your semi-classical velocity, and indeed, when you detect the harmonics, you are detecting the current also from the anomalous velocity. So it can serve not only as a probe for the topological phase in which you are, but it can also be a probe of the local Berry curvature.
Ah, okay.
Because you can excite, for example, you can imagine some setup in which you excite to a given point in the Brillouin zone, and then you try to drive there, and since harmonics are going to be a fingerprint of the velocity of the electron over there, you are going to see what is the Berry curvature, and the Berry curvature is the mother of the lump in topological insulators. So yeah, I mean, in principle, yes. The short answer is yes. We can use this to go, and also to other topological materials, not only Aldan model. So
that was my second question. Is this method already used for topological superconductors?
Topological superconductors, no, but there is a recent paper in I think it's nanolators, in which they have done an experiment in bismuthium selenide, in which they see some kind of evidence that they can see a fingerprint of topology of the edge states in the high harmonic. I don't know if in topological superconductors, but I would assume that yes, because the thing, I mean, high harmonic generation in general is very sensitive to the non-linearities of your system. So when you drive strong enough your electrons, yeah, in principle you can detect things that are beyond the usual linear approximation. So
I see. And just a very small question that so if I understood correctly, through these techniques you are addressing the bulk of the material, but now you seem to say that you can detect the boundary states, the topological boundary states. So is this so?
Yeah, in this experiment, what they show was that they were really seeing what is the effect of the edge states, not only the bulk. Yeah.
Okay.
All the things that I've shown here, it's bulk.
Okay.
But what they've seen is that also the edge states can contribute to this high harmonic response.
Okay, thank you very much.
Okay, thanks, Elsa.
Okay, great. So now we have a question from Artur Slobodenik. Go ahead, please.
Thanks. May I ask you first one question for clarification? Can you come back to the page number 24? And
slide number 24. Okay.
24, yeah.
Okay.
Yes, so it's like about high harmonics in your time binding model. For me, it's interesting how do you calculate it? So it's you calculate the current operator and then average it and look for free harmonics of the current, or how do you do it?
Yeah, so the thing is that, okay, so it's not really a tight binding, it's really a Hubbard model. Okay. And what I do, yeah, I calculate the current operator, and to see the high harmonic generation, you just Fourier transform this dipole operator. Well, the derivative of the current operator, sorry.
Okay.
And that will give you the spectrum of high harmonic generation. In this particular case, I'm showing you the time resolved high harmonic spectrum. So what I do here is a window. So for each time, I just multiply my current operator, for example, with a window function. And this allows you to have kind of time resolved view of high harmonic generation. Instead of seeing what is the spectrum emitted, you just see what is the spectrum emitted at each time, more or less. Mm-hmm. So you just multiply by like a Gaussian, and you do a Gabor transform of your current operator, and then you obtain this, and this allows you to see what harmonics are being emitted at each time. Okay, mm-hmm. That's the thing.
And the second question is, so it's later you're talking about control Wally polarization for the case of monolayers. I think it was a monolayer of tungsten or HBM or
yeah.
What I would like to know, what does it mean, control Wally polarization? I mean,
yeah. So the thing is that, okay, it's here.
So do you modify your bands, or you just populate? You can populate the valleys differently in K.
Yeah, that's the thing. So when we change, you have these omega to omega pulses, And this omega to omega, if you change the relative delay, so it is between them, so the relative phase between them, you just rotate this triangle, okay? So this triangle over here is just rotated by just simply changing the delay between the two pulses, okay? And when the thing is that when you change this phase, you see that you are addressing differently A and the B sublattice, and this in K space translates directly on addressing K and K prime differently. So this is, for example, the effective band structure that we have under the presence of these poles. You see that K and K prime here are not at all affected, but here you close the band gap in K, so you are allowing, and since ionization is strongly dependent on the ionization potential or the band gap, you have more population in K, and here the other way, the other way, yeah. So what you are really doing is, by changing this phase, you are populating more electrons around K or around K prime. So we are really controlling what is the value that you are going to end up by changing this phase. And this is what I see, like changing continuously this phase. I just go from zero value polarization to a maximum when you have this case, and then you go and you totally invert your value polarization at this phase. But I don't know if it answers your question.
But do I understand correctly that your like this Lissajous shaped pulse works in two ways? First, it modifies the band structure, and when one of these frequencies, like omega or 2 omega, populate the conduction band, so it transfer electron from valence to conduction band, or I'm wrong?
Yeah, I mean, when you are really, I mean, the thing is that when you are really changing the band structure effectively, you are closing the band gap, but since you still have some field over there, you can excite.
Okay.
And you will excite, of course, at the minimum band gap. And that's what you are doing. So this pulse is effectively changing the band structure within within the laser cycle, within the laser field. And then, of course, it will choose always the minimum band gap because it's strongly dependent on. So it is really tunneling ionization. So
okay, thanks. Yes, I understand. So you don't need a third pulse.
No. It's just the omega to omega. So the third pulse is just if I now want to read what value polarization I've obtained, I can come with a linear polarized pulse along the gamma m direction. And since I will have some finite hole conductivity, electrons are going to be shifted this way or this way depending on your value polarization. And since the electrons are going to be shifted on up or down, depending on whether you have K or K prime, you will see the ellipticity of harmonics to be flipped upon this flip of value polarization. But this is just to read the value polarization. It's not for, I don't need a third pulse.
Okay.
These two pulses are enough to create value polarization.
Thanks.
Okay, excellent. So it's over 1 o'clock now. I myself have lots of questions too, but there's no time, so I will ask them some of the time. So with this, we're going to close the session. We thank Rui for his beautiful talk and to all of you for your attendance. Thank you very much.
Okay, thank you.